Okay, session two, we look specifically now about nonlinear modeling and performance assessment for frame structures, primarily beams and columns. So topics for this session, modeling and demand capacity calculation for beams and bending, the same thing for beams and shear, and columns, beam to column connections, connection panel zones, and a little bit about diagonal braces. And also do a couple of demos along the way. The scope, we're talking about frame components, beams, columns, coupling beams, diagonal braces, and also beam to column connections. There's a number of different component and element types. And for each component type, and hence for each element type, and hence for the structure as a whole, there's a couple of important things that we need. Reasonably accurate nonlinear force deformation relationships. They're never going to be accurate, they're never going to be exact, but if a beam or a column is exerting some forces on the structure, we'd like the force level to be reasonably accurate. And correspondingly, when we're calculating displacements for the structure, we'd like those displacements to be reasonably accurate, and if only, for example, so that P delta effects are calculated correctly. And so we'd like the stiffnesses to be reasonably accurate also. So a reasonably accurate nonlinear force deformation relationship. Incidentally, we have factors of safety to cover uncertainty, and there always will be uncertainty. And then secondly, we need reasonable deformation and or strength capacities. We'll never know the exact ductile capacity of a plastic hinge. We've got to make some reasonable estimate of what it's going to be. And again, we have or should have factors of safety to cover any uncertainty. Another point is that we must choose realistic demand capacity measures, and it must be feasible to calculate the demand values. I'll talk about this a little bit later on, but it would be very nice to say, oh, yeah, let's use strain as the demand capacity measure. Great idea, except that it's not realistic. You cannot realistically calculate strain. Now, maybe you could establish a strain capacity without too much difficulty, but there is no way that you can calculate a realistic strain demand. You can't do it. It's too sensitive to too many parameters, and you simply cannot calculate a strain demand with any accuracy. Curvature is exactly the same. You might say, let's use curvature. No good, you can't calculate curvature. You can, however, calculate things like hinge rotations with reasonable accuracy. So those become more realistic as demand capacity measures. And then rather obviously the best model is the simplest one that will do the job. And when it comes to nonlinear analysis, as we'll see later on, and particularly for shear walls, a more elaborate model is not necessarily better. So let's look at modeling and demand capacity calculation for beams and bending. We're talking here about a beam in a frame. It's typically going to have some stiff end zone within the column width, and then some clear span distance, and there may be some transverse loads. In Perform, the end zones are assumed to be stiff and elastic. They're not rigid in Perform, they're just stiff, and you can control the stiffness if you want. And any inelastic behavior is going to occur in the clear span region. So really it's the clear span region that we're interested in modeling. And if we're looking at a beam force deformation relationship, don't worry too much about the details here. The top diagram shows the complete beam, and there will be some moment end rotation relationship for the beam as a whole. But the thing we're going to be working on is the moment versus end rotation relationship for the clear span. And the end rotation for the clear span is rather different numerically from that for the beam as a whole, but that's just a detail. And there's going to be some relationship like this. It's a matrix. It's no longer a single stiffness value, but there'll be some, if there's some increment in rotation, there'll be some corresponding increment in moment, and this will be governed by some tangent stiffness values. Once we've got this, we can get all the other structural properties from that. Now, there are 5 models that you might consider using. I'm going to go through the 5 models in order. The first one would be to use an exact model, where you would take a short length of beam, and you could calculate, usually without too much difficulty, a moment curvature relationship for that short length of beam. So it's usually not difficult to get the moment curvature, the MC relationship. Now, if you have an elastic beam, the rest is pretty easy. If you're, for an elastic beam, all you're interested in is this EI value here. The rest doesn't matter. It just goes on forever if it's elastic. So for an elastic beam, if you're given EI, you can use linear beam theory, which is just curvature is M over EI, and you can get the force deformation relationship for the complete beam. And you can use bending moment, usually at the ends, as the demand capacity measure. Very simple. For an inelastic beam, you might say, okay, why don't we just sort of use the nonlinear or the deformation counterparts of bending moment. Let's use a nonlinear moment curvature relationship as shown up here, and let's use curvature as the demand capacity measure. That would be sort of the natural approach, and this would be an exact model. The trouble is it's impractical. It's impractical for a number of reasons, and I can't go into details too much, but in your notes there is some additional documentation on this. Firstly, bending moment is a good strength measure, but curvature is a poor deformation measure. The reason, it's not difficult to get the curvature capacity. The problem, the curvature demand, is very sensitive to the shape of the moment curvature relationship. The key point, there is no reliable way to calculate curvature demand. And see the seminar notes for more details. There are other reasons. Exact theory for a nonlinear moment curvature relationship actually turns out to be very complicated, too complicated for practical application. And in any case, it's not quote unquote exact. If you have a moment curvature relationship which becomes horizontal, and sooner or later it will, exact beam theory will predict infinite curvature, which is wrong. That's not going to happen. So exact theory is not exact at all. It's horribly inexact. So basically, don't even think about it. It's not going to work. The second one is to use a finite element model, and just illustrated here with elements of different lengths. The finite elements use the moment curvature relationship for the beam. For a linear moment curvature relationship, you know that the finer the mesh, the more elements you use, the more accurate the solution. It approaches the exact linear theory. So you might say, great, okay, if for nonlinear behavior, let's just refine the mesh and we'll get more accurate results. Doesn't work that way for nonlinear. One reason is that as the mesh is made finer, the calculated curvature will get larger and larger and larger. And the smaller you make the mesh, the maximum curvature will just get bigger and bigger. It's very sensitive to changes in the finite element mesh. It's also sensitive to a number of other things. If you really want to be exact or nonlinear, you have to use a lot of really complicated fracture mechanics theory. It's not simple nonlinear behavior anymore. It's much more complex stuff, which is way beyond anything which is practical. So a finite element model may be good for linear, not so good for nonlinear. I'll say more about this later on when we talk about walls, because a similar issue comes up. A couple of other issues: it can be computationally expensive to use this finite element model. You can use it in Perform 3D if you wish, but as a general rule, this is not practical and is not recommended. The third model is a plastic hinge model, and this is just illustrated here. In a simple case, you have an elastic beam with a plastic hinge at each end. This is the column face, by the way, because we're looking at the clear span. A plastic hinge is literally a zero-length hinge, very much like a rusty hinge. It's rigid until you reach a certain moment, and it rotates. Then you push it back the other way, it locks up instantly, and then it'll rotate in the other direction. It's almost exactly like a rusty hinge. So it's initially rigid, and then it becomes nonlinear. The key point is you assume in this case that all of the inelastic deformation is concentrated in these hinges. This is an elastic beam, so you have concentration in the plastic hinges. That's approximate, very approximate, but from a practical point of view, it actually is a pretty damn good way of doing it. And realistically, this is about as good as you can get. The deformation measure is also quite simple. It's hinge rotation. If there is a problem if you have gravity loads, and it's indicated here, if you have not very much gravity load, so as your bending moment diagram when hinges form is like this, it doesn't matter, that's pretty close to straight. Anyway, you know the hinges will form only at the ends. If you have much larger gravity load, you could get the maximum bending moment near the middle, and you might have to use some additional hinges to capture that. This does get to be a problem. One of the problems indicated here, if you have hinge formation in the middle, and you push the structure in one direction, the hinges will form in the middle. If you push the structure back in the other direction, they'll form, and they'll form in the same direction, so the beam will sag some more. This way, it'll sag some more. This way, it'll sag some more. It'll progressively sag under cyclic loading, and you probably don't want to have that happen. So it's a good idea to avoid having hinges form in the middle anyway. Just incidentally, a plastic hinge model can be used for a reduced beam section. It's actually a natural application for a plastic hinge model. Is the center of the RBS would be here and here, and this is where you might position your hinges. And it's a natural application of the plastic hinge model. If you have some experimental results, you can process them to give the required hinge properties. I would, though, be careful because I've seen papers where the values are processed to give hinge rotations not at the center of the RBS, but at the face of the column. And in that case, you would need to put the hinge at the face of the column. But I think the more natural thing here would be to calculate the equivalent hinge properties at the center of the RBS section and position the hinge at that location. The fourth model is a plastic zone model. And instead of assuming a zero-length plastic hinge, we now have at each end a finite length plastic zone, but with an elastic beam in between. So the inelastic behavior now occurs within a finite length plastic zones at the ends of the beam. Now, in a real beam, you will get sort of plastic zones, but the sort of thing happens in a real beam, they kind of spread. They're not fixed in length. And there have been some theories that seek to model the behavior in terms of a plastic zone which changes in length, but they're awfully complicated. They're really too complicated for practical application. So practically, I think you have to go with a fixed plastic zone length. The issue is how long should it be? I'll talk about that in just a moment. Deformation measure. You can either consider the average curvature over the plastic zone, or you can consider the rotation occurs within the plastic zone, a lot like a hinge rotation, and that's just the average curvature times the plastic zone length. So it's quite easy to calculate a demand capacity measure for this model. The big issue is the plastic zone length, and there's a really important point here is that you have a moment curvature relationship for the beam, or possibly you've used a fiber cross-section, which means that you're calculating a moment curvature relationship during the analysis. But there is a moment curvature relationship for the beam, and this is what you have to use in the plastic zone. And so you can't sort of arbitrarily pick a plastic zone length and then use the actual moment curvature relationship. I think you can kind of see if you use different plastic zone lengths and the same moment curvature relationship, you're going to get different behavior for the beam as a whole. So what you have to do is to pick the plastic zone length, which enables you to use the moment curvature relationship for the actual beam. And there's a basic rule for this, 0.5 times the beam depth. It's really rough, but actually it's probably not bad. And for practical purposes, it's probably about as good as you can do. There are a couple of ways in which you can do this and perform. I'll demonstrate this later. You can either use a curvature hinge that uses a moment curvature relationship, or you can use a fiber cross section in the plastic zone. In that case, the moment curvature relationship follows from the behavior of the fiber cross section. I'll talk about that a little bit more later also. Here's what a fiber section for a beam might look like. You simply divide the beam cross section up into a number of fibers, and you assign locations and areas to the fiber, and the moment curvature relationship follows from the fiber behavior. And the beam is assumed to be elastic for horizontal bending. In Perform, you can specify a variety of different material types for the fiber properties. You can use a concrete type material, a steel type material without buckling, a tension-only material, or material with buckling. You can specify a variety of different material types for the fibers. There's quite a lot of flexibility. Again, though, I'm not going to go into. I will do some examples later on, incidentally, of a fracturing connection model using a fiber beam. Plastic zone length. Don't worry about this. You can look at this in your notes. Pauly and Priestley do give a more refined recommendation for the plastic hinge length based on experiments of bridge columns, and it gives you this formula here. Let's not worry about the details. The last model is the chord rotation model, and the key thing about this one is that the force deformation relationship is now directly in terms of end moment and end rotation. Just moment versus end rotation. No plastic hinge rotation, no curvatures, just the overall behavior of the beam directly. If you look at the end moment versus end rotation relationship, the initial stiffness here is, it's basically 3EI over LI, assuming that this inflection point is at this location and is pretty much on the chord joining the two ends. And if this is in the middle, you're probably familiar with this, it would be exactly 3EI divided by L over 2 would be 6EI over L, which is a common number. And then from there on, it becomes nonlinear. Perform implements this, I'll show later, using a thing called a FEMA beam model, which exactly implements the chord rotation model. And the same thing for columns. The reason why it's called a FEMA beam is because this is the only type of model which is actually covered in FEMA 356, or what is now ASCE 41. So looking a little bit more at the chord rotation model, basically it assumes that the hinges at the middle and the moments are the same at both ends. Strictly speaking, it applies only for that case. But you can apply it for other cases. And somebody asked me earlier, why, when you use a FEMA beam model, do you have two of them, one at the left end and one at the right end of the beam? The reason is that the moment strengths may be different at both ends, and also enables you to put the inflection point somewhere other than the middle of the beam. And so you have two of them, one at each end, and they can be different if you like, or they can be the same. So strictly speaking, it applies only to symmetrical beams, no transverse load. However, it's usually reasonable to assume an inflection point at midspan. Even if the beam is unsymmetrical, why not sort of assume it like that? It's good enough for practical purposes in most cases. Often the transverse load is not very large, doesn't have much effect. If it does, you can't really use this model. And the deformation measure now is directly the rotation from the chord. Theta is shown in the diagram there. And notice that if it was hinge rotation, it's like the plastic hinge rotation. Here we're kind of talking about the total end rotation. Now let's, those are 5 different models. I'll say a little more about them in a moment. Let's come back and look at capacities. And we've shown this diagram before. The ASC deformation capacities. IO capacity is usually the onset of visible damage. CP typically at the ductile limit, and LS typically maybe 75% of that. And you can use this for components of all types. And for example, if you have some experimental results, you could use this relationship to get appropriate deformation capacities. And ASCE 41 gives capacities for many different components, but for beams and columns, it gives capacities only for the chord rotation model. If you want to use a plastic hinge model or a plastic zone model, or heaven forbid, a finite element model, you have to do a little of extra work to determine what the capacities might be. Here are some examples of the ASCE 41 capacities for chord rotation. And this is the ASCE 41 moment versus rotation relationship. Yield rotation, plastic rotation is measured from the yield rotation. And these are expressions are in terms of plastic rotation rather than total rotation. Steel beam and a reinforced concrete beam. Steel beam first. ASCE 41 gives the capacities as in terms of a ratio of plastic rotation to yield rotation. So for IO, it's 1, which means you can get to double the yield rotation. Life safety 6, you can get to 7 times yield rotation total. CP, it's 8, means you can go out to 9 times the yield rotation total. And it does vary with axial force, as we can talk about later, but ASCE basically does this for all beams, regardless of the span to depth ratio and things like that. And this is just an example that ASCE 41 in its current form is really a little crude. So this is a one-size-fits-all type of capacity. It's probably going to get more complicated as time goes by. Reinforced concrete beam is a little more complicated because it's a common sense thing, is if you have a high shear force at a plastic hinge, that hinge is going to be more brittle than a hinge which has got a low shear force. So it's going to have a smaller capacity. So if you have low shear, the ASCE 41 now gives you this as a total value in terms of rotation, not as a ratio. 1% for IO, 2% for LS, and 2.5% for CP if you have low shear, and rather smaller than that if you have high shear. Another thing you see here is these are really rather crude numbers. They're sort of 1.5 significant digits. This is a very complicated process to determine appropriate capacities. And ASCE 41 doesn't say you have to use these. It says you can use these if you want to, if you have experimental data available to you to justify other values, you could use other values. But do notice this one thing, that the capacity is dependent on the shear force, which is rather important. Let's compare steel and concrete, and I just took here a W27 by 94. I don't know where I got 23 feet from, but if you look at from the previous slide, calculate the rotation capacities and compare the steel and concrete. The plastic rotation capacities for steel member based on ASCE 41 would be IO 2067. Incidentally, there's a typo when you're in the printed thing here. It's got 0.067, but you can fix that. The concrete one is 0.01, so rather a little unusual. The ASCE 41 allows for the IO case, rather larger hinge rotation for concrete than steel. For life safety and collapse prevention, there would be 0.40 and 0.54. These are roughly double the values for reinforced concrete. So some complications. Firstly, steel beam capacities. The values I just showed were for compact sections. If the section is non-compact, it's smaller. And if the axial force is large, typically this won't matter for a beam, but it certainly does for a column. The larger the axial force, the smaller the ductility. You tend to get buckling sooner. So the rotation capacity can depend on the axial force. Large compression axial force, smaller rotation capacity. Concrete beam, smaller if the shear force is large, and also if the axial force is large. So the rotation capacity for a concrete beam hinge can depend on both the shear force and the axial force. And I'll refer you to ASCE 41 for details. Summary. Practical models for beams. The chord rotation model, you would use this as the first choice. The main reason being that ASCE 41 will give you some capacities. It's also the simplest model. If that doesn't work, use a plastic hinge model. That doesn't work, use a plastic zone model. If it doesn't work, you might consider a detailed finite element model. but I don't think you'd ever consider using exact beam theory. Let's say a little bit more about fiber sections. I showed a fiber section for a beam just before. They don't apply for the chord rotation model. A plastic zone is a little bit like a hinge. If you want to use a fiber section, you have to use and perform a plastic zone model. And this would be the most likely use, I think, of a plastic zone model. If you have a zero-length hinge, you can approximate it using a very short plastic zone. Now, typically, I think you would use a plastic zone about 1/2 the depth of the beam, but I will show later on an example where you have a fracturing connection, a pre-Northridge type connection. And that's, it's kind of like a hinge, but you can model it as just being a very short plastic zone. You can use fiber sections for finite element exact models also. It's rather more expensive computationally than a hinge model, and so you'd only use it if you really felt it was necessary. It's another little bit here, and some engineers feel that this is really an important effect, and I'm inclined to agree with them, and it's something we need to be aware of because this is something which doesn't happen in linear analysis. If you have a reinforced concrete beam, then as it cracks, the neutral axis will shift to the compression side. Here's the center of the beam, the neutral axis will move up to here. In an elastic beam, the neutral axis would be in the middle, but it moves upward. So the axis of the beam has to extend. If it can extend, it will, and the beam will grow in length. If it can't extend, if for some reason it's confined by a very stiff column, for example, or possibly by a floor slab or something, then it has to go into compression. And it becomes rather like a pre-stressed beam, and it becomes stronger.